1.4 and 1.5. And I'm not, this isn't super detailed or anything like that, but something you need to know from 1.4 is the definition of continuity at a point. And that would be on page 70 in your book, but 1.4, it should be in your notes too. Actually, it's on the videos too. I know it's one of the first things I talked about in the notes. What does it take to be continuous at a point? Basically, it has to have a f of c, okay? It has to have a closed dot. So f of c has to exist. Right there it is, f of c, it's a closed dot. Okay, the limit as x goes to c of f of x has to exist. Okay, so the limit, that limit exists because they're both sides go into the same y value. And then third, f of c has to equal the limit as x goes to c of f of x. So the dot has to be at the same place that the lines are going to, and then it's continuous. Which should make sense. Can I draw that without lifting my pen or pencil? Yes. But this is the mathematical definition of being continuous at a point, the three things that have to happen. So if you're ever asked, like, why isn't it continuous there, it's one of these three reasons that would fall apart. Maybe there's no closed dot. Maybe the lines, don't go to the same spot, or it's unbounded behavior. And maybe it's just the fact that the limit and the function value are not the same. And there are pictures of that in your book, and I gave also visualizations of these three examples of where it falls apart. You also had a homework problem regarding that too. The homework problem that you could refer to for that would be problem number 87 on page 81. Is a good problem referring over the definition of continuity. All right. So then also in 1.4, you had to be able to discuss continuity. Okay, so you had to be able to discuss the continuity of a function, whether or not a function is continuous, where is a function continuous, where is it not continuous. And there were a lot of different functions that I went over in 1.4. For example, I went over functions that were of this form in the notes. This was always equal to a piecewise function. -1 if x is less than a, and +1 if x is greater than a. This was in the notes. And so if you're ever asked to discuss the continuity of this type of function, you know that at a it's not going to be continuous, because the graph of this function, and a is a number. A is any number, like 2 or 15 or 27 or 6 or 1 or 0 even. You know that right at a, here's a, is the split up point. Everything above a is a +1. And everything below a graphs as a -1. So this wouldn't have a limit at a, but if you were looking for a one-sided limit, say like the limit as x goes to a from the negative, how do you, if you were just looking at this, how would you tell which one of these to look at from the negative? Which side is from, which one? Less than a is from below it. Okay, so what would this limit be? -1. But what if I wanted the limit as x goes to a from the positive? What would it be? 1. And what would the limit as x goes to a be? Does not exist. Why not? Different limits from left and right. Okay, so that's one of the examples I went over. Another thing that you'll have to know, what type of function is this if you graph it? It's steps. It is a step function. This is the mother of all step functions. It has steps of length 1 that are 1 unit apart. Okay? It starts at the origin. Tell me, is this a continuous function? No. Okay, where is it continuous? Where is it continuous? Continuous everywhere except every integer. Integers are those positive and negative whole numbers. Okay, so does that only apply to this function? What if instead of that greatest integer function, I have something like this? Whoa, that one's really hard, isn't it? What did I just do to that function? Shifted it which way? To the right. 72 units. Doesn't it still look like this? Except this would now be 72, and this would be 73, and this would be 74. Where is it continuous? Everywhere except every integer. It's the same every time. Just because I subtracted 72, what if I added 53 instead of subtracted 72? Where would it be continuous then? The same exact thing, okay? It's not hard. All right? Piecewise functions. Everybody loves piecewise functions. Okay, right? Give you a piecewise function, you're happy for a week, right? Where are these things continuous? This is a homework problem I know you've done. Okay, you have to figure out where is that continuous. You're like, oh my gosh, that's impossible. No. Will this all by itself be continuous? Yeah. Okay, would this all by itself be continuous? Why? What kind of functions are those? They're parabolas. They're going to be continuous. Okay, so what about this would make it not continuous? Right there. At 2 might be the only place it's not continuous. What has to happen for this to be continuous at 2? What has to be equal? Yeah, these two have to be touching when x is 2. So these two have to be equal when x is 2. So all you're doing is just checking to see if that's the case. Put 2 in for those x's. And put 2 in for those x's. And see if you get the same number for both. What do you get? 4 minus 8 is negative 4, plus 6 is, and what's this one? Is it continuous everywhere?
Yeah.
Yep, it's continuous everywhere. What if those two would, like, this one would, what if that one would have been 0? We aren't finding a limit. Where? So, but what if you had to say where it was continuous? Except 2. Okay. All right. Removable discontinuities. How do you find removable discontinuities? So what if I've got x minus 1 over x squared plus x minus 2? There's my function. Any removable discontinuities there? Okay, basically I'm setting, what am I actually finding when I set the denominator equal to 0? All possible discontinuities. So this is finding all possible discontinuities. Okay, so I'm going to factor it, x plus 2, x minus 1. What are all possible discontinuities? X equals and x equals 1. And actually these are both for sure discontinuities, okay? But which one's removable? X equals 1 is removable. So in other words, what would it be on the graph? What's another word for a removable discontinuity? It's a hole. A removable discontinuity is otherwise known as a hole. And this would be just a discontinuity, a non-removable, okay? But it's a discontinuity, but what is otherwise known as a vertical asymptote? That's from 1.4. We're just applying some of it from what we learned at 1.5. They're the same thing. We found them the same way. All right, the next thing in 1.4 was the intermediate value theorem. The intermediate value theorem. Here are the things you have to check for the intermediate value theorem. First, you must say, number one, you have to state that f of x is continuous on whatever interval you're given from a to b. Second, you have to find f at a and f at b and show what they are. And then, depending on what they ask you, but mostly likely they'll tell you to say something like, find where f of c equals 4. So they'll give you some function like, say, oh, I'm going to pick a different one. I'm going to say f of c is 11. No, I'm not. Yeah. So show where f of c is 11. And here's my function that I'm given. F of x is x squared plus x minus 1. So I want to apply the mean value theorem. So the first thing and my interval is 0 to 5. So the first thing I say is that this is continuous on the interval from 1 to 5. And it is because it's a parabola. Okay, and then I find f of a. What's a in my problem?
0.
So I'm going to find f of 0, which is -1, and f of 5, which is 25 plus 5 minus 1 is 29. So what this is saying, visually, here's what this is saying. When I put 0 in, I get the y value of -1. When I put 1, 2, 3, 4, 5 in, I get the y value of 29. Somewhere in between here and here, didn't the y value have to be 11? Didn't the y value have to be 11 somewhere to go from -1 to 29?
Yeah.
I want to find out what x value that happened at. So the way that I do that is I set my function, f of x, equal to 11. But what am I going to replace the x with? C. So I'm going to set, first I start with f of x, and I want to find where f of c equals 11. So I'm going to change all of these to c's, set it equal to 11, and now I'm going to solve it. How do I do that? Bring the 11 over. I have to get it equal to 0. Don't try to factor unless it's equal to 0. Your factoring is a waste of time then. And now I can factor what multiplies to be -12 and adds up to 1. -3 plus 4. So C equals 3 or C equals -4. Which of those is in the interval that I was given at the beginning? What's my interval? 0 to 5. Which of those numbers is in the interval from 0 to 5? So my C is 3. And I've applied the intermediate value theorem. All right. And we kind of just reviewed the other section when we went over the notes. So that's pretty much a little review. What you can use on the test, you can use a page of notes that you write, front and back. I recommend that you watch all the videos, again, from 1.4 and 1.5. And on your homework assignment, there's a slight little change on the homework assignment that I had for you, if I can find it fast. I have too many papers here. Okay, here we go. All right, on number 17, there's no optional practice test, and just do 47 through 64 instead of 47 through 70. Yeah, but the other parts still do. 31 through 44,